Hello students, let's begin with a simple thought. Why does chloroform behave so differently from methane, even though both are just carbon compounds? The secret lies in the carbon-halogen bond. And Lt, break time is equal to 0.5 s and Gt. Halogens are more electronegative than carbon. So, in a carbon-halogen bond, the electron cloud shifts towards the halogen. The carbon acquires a partial positive charge called delta plus, and the halogen acquires a partial negative charge called delta minus. And Lt, break time is equal to 0.5 s and Gt. This polarity makes the carbon site electron deficient and highly reactive towards nucleophiles. Remember, the polar nature of the carbon-halogen bond is the key to most reactions of haloalkanes. Now let's talk about bond lengths. As we go down the halogen group, the atomic size increases. This causes the carbon-halogen bond to stretch. For example, the carbon-fluorine bond has a length of 139 picometers, the carbon-chlorine bond is 178 picometers, the carbon-bromine bond is 193 picometers, and the carbon-iodine bond extends to 214 picometers. And Lt, break time is equal to 0.5 s and Gt. Notice how the bond lengths increase as we move down the group from fluorine to iodine. And Lt, break time is equal to 0.5 s and Gt. Shorter bonds, like the carbon-fluorine bond, are stronger, while longer bonds, like the carbon-iodine bond, are weaker and more prone to breaking. This trend directly affects the stability and reactivity of these halides, which is shown clearly in the figure. Bond enthalpy is the amount of energy required to break a carbon-halogen bond, and it tends to decrease as the halogen atom gets larger. Let's take a look at how the bond enthalpies compare. The carbon-fluorine bond has the highest bond enthalpy at 452 kJ mol superscript 1, making it the strongest among the carbon-halogen bonds. And Lt, break time is equal to 0.5 s and Gt. The carbon-chlorine bond follows at 351 kJ mol superscript 1, still strong but not as much as the fluorine bond. The carbon-bromine bond has an enthalpy of 293 kJ mol superscript 1, much weaker. And Lt, break time is equal to 0.5 s and Gt. Finally, the carbon-iodine bond is the weakest, with an enthalpy of only 234 kJ mol superscript 1. This trend shows us that as we go down the halogen group, the bond strength decreases. And this is why alkyl iodides, with their weaker carbon-iodine bonds, are much more reactive than alkyl fluorides, where the bond strength is much higher. And Lt, break time is equal to 0.5 s and Gt. The figure on the right also summarizes these bond enthalpies, showing how the C-F bond is the strongest and the C-I bond is the weakest. This decreasing trend in bond strength explains why C-I compounds undergo faster nucleophilic substitution reactions compared to C-F compounds, which require more energy to break the bond. Now comes a fascinating twist. You might think that the carbon-fluorine bond, being the most polar, would have the highest dipole moment. But the actual values tell a different story. And Lt, break time is equal to 0.5 s and Gt. The dipole moment of the carbon-fluorine bond is 1.847 dB. The carbon-chlorine bond is slightly higher at 1.860 dB. The carbon-bromine bond is 1.830 and the carbon-iodine bond drops to 1.636. And Lt, break time is equal to 0.5 s and Gt. This happens because dipole moment depends on both electronegativity and bond length. Even though fluorine is the most electronegative, its bond is so short that the product is slightly less than chlorine. So, the carbon-chlorine bond shows the highest dipole moment. Let's see how these properties explain reactivity. Consider the hydrolysis of methyl iodide compared with methyl chloride. And LT, break time is equal to 0.5 SNGT. Methyl iodide, written as CH3I, reacts with hydroxide ion in water to give methanol and iodide ion. We say CH3I plus OH minus aqueous gives CH3OH plus I minus aqueous. And LT, break time is equal to 0.5 SNGT. Methyl chloride, written as CH3Cl, undergoes the same reaction but much more slowly. The reason is clear: the carbon-iodine bond is weak and breaks easily, while the carbon-chlorine bond is stronger and resists breaking. And LT, break time is equal to 0.5 SNGT. Thus, the reactivity order of nucleophilic substitution is carbon-iodine bond greater than carbon-bromine bond greater than carbon-chlorine bond greater than carbon-fluorine bond. Now let's connect these trends to real life. The strong carbon-chlorine bonds in PVC, polyvinyl chloride, make it durable for pipes and flooring. The weak carbon-iodine bonds in alkyl iodides make them very useful reagents in organic synthesis because they break easily. And LT, break time is equal to 0.5 SNGT. Solvents like chloroform and dichloromethane rely on their dipole properties for dissolving organic compounds. And LT, break time is equal to 0.5 SNGT. And in pharmaceuticals, introducing a carbon-fluorine bond can improve drug stability because this bond is the strongest and resists metabolic breakdown. So, to sum up, the carbon-halogen bond is polar with delta plus on carbon and delta minus on the halogen. Bond length increases from carbon-fluorine to carbon-iodine, while bond enthalpy decreases in the same order. The dipole moment is highest for the carbon-chlorine bond, not carbon-fluorine. And LT, break time is equal to 0.5 SNGT. The reactivity trend in nucleophilic substitution follows bond weakness: carbon-iodine greater than carbon-bromine greater than carbon-chlorine greater than carbon-fluorine. And LT, break time is equal to 0.5 SNGT. These simple facts explain both chemical reactivity and industrial use, from strong plastics to reactive laboratory reagents. I hope today's session helped you see how even one bond, the carbon-halogen bond, can control so much of organic chemistry. See you in the next class for more exciting concepts.